Okay, guys, let's dive right into chapter 6, physics video. Uh, I now have to differentiate between my videos. I will have to start saying physics video or math video because I have started to upload some algebra videos. So, let's start with the first video of chapter 6, right? We just finished off chapter 5, which we know was Newton's second law, and now we're going to go into chapter 6, which is Newton's third law, right? So basically, the title of that law is action and reaction. So I always kind of think of consequences, like if you do this, something's gonna happen. Kind of like your parents say, like, oh, if you shoot your airsoft gun in the house, you'll get grounded, something like that. Whatever. Action and reaction. I say so. So in terms of physics, though, the third law states that I'm just gonna write it all out. It's gonna be a mouthful, but whenever one object whenever one object exerts a force on a second object, and again, I'm getting this from page 75, so you can follow along. Force on a second object. Let's call this A. Let's call this B. Second object is B. Um, B will exert an equal and opposite force on A. Sorry for a lot of writing here, but basically that means, let's say, if I kick a soccer ball, or let's say I kick a soccer ball, okay, and I go here, okay, and I kick it and it goes flying. Let's say I exert 10 newtons on that soccer ball. Guess what? The soccer ball also exerted 10 newtons on my foot. That's what this says, right? So that's pretty interesting. Action and reaction. So that says so the way I like to think of this as well is it's also on a diagram or a picture on page 75. It's this girl jumping off of a canoe onto a dock. And so if you have like a canoe here, okay, okay, if you have like a canoe there and then like here's the dock that she's jumping to or whatever, okay, and if she jumps off, okay, this is going to be a bad drawing, but if she jumps off, right, she's kind of pushing off with that foot, she's going this way, then she's going to exert a force on the boat. So the boat's going to move backwards. The boat's exerting a force on her foot, and she's exerting a force on the boat. And that's just how it works. When she puts a force down, the boat's going to go backwards because, it's sitting in water. So I like to think of that. Um, say you have a car here. This is a very interesting one that I found is fascinating. This is going to be an awful drawing of a car, okay? It's terrible. But then let's say there's this little tiny bug coming along, okay? His little wings, and he's flying along. And let's say this car's going 80 miles per hour, right? And the bug hits the windshield, it's just going to go splat, right? That's dramatic, but it's just going to splat on the windshield. The car won't slow down noticeably. The car won't slow down noticeably. It won't even feel anything. It'll just be splat on the windshield. Well, believe it or not, the force that it seems like the car exerted this massive force on the bug. 'Cause the bug just blew up, right? But it turns out the force that the car exerted on the bug is the exact same of the force that the bug exerted on the car. The forces were the same, which I think is just fascinating. Equal force. But the reason that the bug went splat and the car didn't even, be altered is because the car has so much more mass. So that's really cool. Now, let's dive into 6.3, which is identifying action and reaction, which is very, very easy. You shouldn't have any trouble with this. But it's basically saying, well, okay, Newton's law is action and reaction, but what are the actions and what are the reactions? So, they define action as object A exerts a force on object B. Force on B, right? Then reaction is B exerts a force on A. Force on A. Okay, so it's that simple. So let's say we have, go back to the car diagram with the bug, right? Again, a very lame car. Let's call this A. Let's call the bug over here B. When they come together and when they hit over here down this another time frame, you have the bug on the windshield there. Okay? So the action force would be A, the car slamming into the bug. And that force is some number. Let's call that 10 newtons, okay? It's not realistic. Let's call it 10 newtons. So that's the action force. But then the reaction force is going to be equal. These two are equal to each other. So the force that the car exerts on the bug, is going to be the same that the bug exerts on the car in this diagram. It's still going to be 10 newtons. So that's really interesting, I think. So that's identifying. Now, action and reaction on different masses, we kind of talked about here. So if two things come together in an action and reaction force diagram like this, and one has a much larger mass, the one with the smaller mass is going to be affected more, whether it's splatting on the windshield or flying backwards. There's many different options. So they give the diagram with the cannon there, and let's draw a little cannon here. Okay, let's see if I can draw a cannon. It's gonna be a bad cannon. Alright, so there's my cannon. Okay, don't laugh at my cannon. Alright, and let's say, so when the cannonball is shot out of it by the gunpowder, there's a huge force this way, but there's also a force this way. Oops. It needs to be straight. Oh, I don't know what I just did there. What is going on? Alright. Well, let's just redraw it then. Needs to be a straight line like this, and they're equal. These two forces are equal, right? But since the cannon itself has such a larger mass, then the cannon is gonna maybe jolt back a little bit. It's gonna have a little recoil, but the cannonball is gonna go super far. It's gonna go like, hundreds of feet away, more. So since the mass of the cannonball, the cannon, is so much bigger than the mass of the cannonball, then the force is the same. The acceleration is much, much more for this cannonball than this cannon itself. So that's really interesting. You can see that cannonball, you have force, then you have small mass, small m, is equal to a big A. That's cannonball. And cannon, you have the same force. You have a much bigger mass. Oops. Wow. Why did I do? Much bigger mass equal to much smaller A, right? That's just how it works. It's inverse proportion. As mass goes up, acceleration goes down. So we're just kind of blowing through this chapter really quickly here. I kind of like this. Do action and reaction forces cancel? Let's take a look at that. All right. Well, so when you have, so they only really cancel if there's two opposing forces. So let's take that diagram that they have with the guy kicking the football. Okay, so you have a foot here. It's more or less a foot. Okay, and he's kicking this football. Okay, and B, A. So A exerts a force on B. B goes flying because A has more mass than B does, right? So we know that. But then let's say that there's 2 feet in this game, and here's B. And then, oh, here comes along C, right? There's C. C, A, okay. Now, if C and A are equal forces, then yes, this is going to cancel out, and B will go nowhere. But they have to be exactly equal and opposite forces to cancel out here. Because then that will cancel out, and B will go nowhere. Nowhere, right? So that's pretty cool stuff. And then I guess the next video will be devoted to the horse cart problem, which really will solidify your knowledge of this. And there we go. That was a quick demo of 6. And the only reason I say it's quick is because I think 6 is pretty easy to grasp. So I don't feel like I needed to do too much to explain it. And yeah, there you go. We'll be moving on to 7, which is a great chapter, which is all about momentum. And I find that to be one of the most applicable chapters in real life, so I can't wait to see you guys there.